Okay, hello everyone. It's great to see you after such a long period of time. Um, Last time when I was on a real conference was over 2 years ago. I've done some drag meetups along the way, fully masked, and that felt a bit weird. But this feels a bit weird as well, so I hope I can survive next 50 minutes. I am terrified. Anyway, so since I am so stressed, I thought I could tell a joke, a COVID joke. But I changed my mind because I figured out that you might not get it in the next couple of days, right? Yeah, real pandemic, isn't it? Okay, so bad jokes aside, my name is Grzegorz Piwowarek. I work for Hazelcast. Here's my Twitter handle. I'm a lead architect at Hazelcast. It means that I work for the CTO office. I'm technically not bound to any particular team, but in practice I am. So last couple of months I spent exclusively with the Hazelcast cloud team working on the new serverless product, which I will tell you a bit more tomorrow. Besides that, you can catch me doing some trainings all around Europe and writing some blog posts on my site. Well, to be fair, it was neglected for a while, but I'm coming back to that. And by the way, if you want to ask questions, you know the drill. You go for the Slido. So the topic of today is CompletableFuture. But I won't be focusing on basics. That's something that you can pick up easily, and there are better sources to learn that. But unfortunately, CompletableFuture has a lot of interesting corner cases. If you think about things like a threading model, cancellations, and a few other helper methods that are available in there, it turns out they are way more funky than you would expect. And whenever I deliver workshops, pretty much everyone is always surprised. So I thought we could take and gather it all together into one place. I'll try to do some live coding, so we'll see if the lead architect can still code besides doing just Google Docs presentations, Google Slides. Sorry, even that I messed up. Okay, so what's the main difference? When you write synchronous code, when you write imperative synchronous code, everything is easy. You write lines, and the code executes the same way it's laid out on a piece of paper or whiteboard or whatever else people nowadays write code on. Suddenly, when you introduce asynchronicity into that, there is a totally new dimension and temporal dimension that you need to take into consideration when understanding and writing it. Because things can be happening in the background. And this makes things much harder to reason about. And not even thinking about some concurrency edge cases. Just reasoning about code which happens in the same time is much harder. So the main difference between async and sync is that async is happening more or less in the background, and you don't have direct control over when it ends, when it returns some results. So if we are running some method asynchronously, how do we get a result back? And the solution is pretty easy. So there is a concept of the future, promise, or there are a few other names around the place. And the idea is pretty simple. You call some method, you receive an object, that's a return value, but that return value is not the actual return value you care about, but more like a container that will spawn that value that you actually care about at some point in the future, hence the name. So if you actually want to wait and get the actual result of the operation back, you call .get on an old school future, you block, and you just wait. But while you are blocking and waiting, you can do something else. And that's the whole point of that. And the good news is that any method can become async. All you need to do, effectively, is to create your own executor in your thread pool, submit something into that, and then just wait for the result. And Java has two implementations of the future. So in the JDK 1.5, there was the basic future, and in 1.8, CompletableFuture was introduced. And why is that? Because if you start looking at the standard Java future, let me code that quickly. Let's give it just one thread. If we submit something to a future, to a thread pool, you obtain a future. And let's have a look. What do we have at our disposal? So there is this get method. There are those helper methods from IntelliJ, so ignore that. There is a get with timeout. There is a cancel. There is canceled and is done. And that's pretty much all our API. And if you start thinking about what you would like to do when some operation is being executed asynchronously, it's probably much more than that. So first things first, probably I wouldn't like to block on a future, but let's say just define that whenever this object is computed, just run something there. Or perhaps I want to combine something more sophisticated and say, let's say I'm writing this currency exchange or something, and I'm using multiple providers, and I really care about low latency, so I issue 3 parallel requests, and I want to return the first one that actually matters to me, the one that arrived the fastest. How do you do that here? It's not obvious. Actually, if you control the side that actually triggers the computation, then it's okay. You can figure out, okay, I put a queue here, so whenever this operation completes, I actually don't care about the result, but I take results from the queue. It becomes complicated. So as you can see, with only those few methods at your disposal, it's really hard. And now start thinking about, so we know about composing futures. We thought about, blocking. But there's also limited exception handling capabilities. Because if you call .get, the exception can be thrown, and that's pretty much all that you can do with that. And that's pretty bad. So this is where actually Google Guava came in with, to help us. They prepared this listenable feature, which was slightly better than the normal feature because you could register callbacks on that. But it wasn't still perfect. It was before JDK 8, so there were no lambdas. It was before 2014. So you would need to write your anonymous classes, which were, well, technically speaking, it's still a lambda, just a very bloated one. So as you can see, the experience was better than with the standard feature, but still highly suboptimal. And in JDK 8, the huge revolution arrived. CompletableFuture, the ultimate solution to your asynchronous problems in Java. And it's pretty good. It's pretty good, I like it, but there are some design decisions, there are some methods that work not just like you would expect them to. And this is what we'll be talking about. If you want to see how the typical flow looks like, it's like imagine you create 2 futures. You call 2 different asynchronous methods. You get 2 futures. And now you can enjoy this nice declarative style of programming. So that's this kind of monadic style where you don't worry about what's happening internally, but you just express your will, and that's pretty much all. You don't need to think about some complex queuing mechanisms, how to get those results back. You say, then apply, and increment that value, or rather derive a new value that's a +1 than the previous one. Then combine with a second feature, and when they arrive, apply that transformation on top of that. And at the end, run something else. But that presentation is not about the basics. We will just look about those key peculiar parts. If you want to learn the basics, you have better sources for that. So the first things I'd like to talk to you about today is the concept of cancellation of futures. So if you have a look at this one, it is an old school executor service, old school future. You submit something here. Let's call that a future, actually. You get this option to cancel it and provide a parameter which is called may interrupt if running. So as you would expect, it will try to interrupt the operation, the thread that was running, backing that operation. Let's have a look inside. What's in there? There are, of course, many implementations here. There's an abstract future. If you dig deep inside, you'll end up seeing interrupt task, checking if interruptions, and you can see that actual. And if you dig deeper, you'll find something like runnable future. And it's an interface that combines both a runnable and a future. So it's both a task that's being run. At the same time, it's a future which is represents a result of the task that's being run. This makes it really easy to interrupt, because you have this clear one-to-one mapping. So if you cancel, the thread gets interrupted, and here you go, as easy as it goes. And the first thing that usually surprises people is that if you have CompletableFuture and you try to cancel it, wait, before I show you, let's actually look at the documentation. So here we have a basic CompletableFuture. Let's make a CompletableFuture of integer. Let's try to cancel it. As you can see, the CompletableFuture, it implements the same set of interfaces as the main future. So you can always get those get, cancel methods as well. So you provide may interrupt if running, and voila, we canceled our future. But did we? Let's have a look at the implementation. If you look at the implementation, or rather the documentation, may interrupt if running, this value has no effect in this implementation because interrupts are not used to control processing. So the thing is, CompletableFuture introduced a totally different paradigm. So in the past, we had this convenient setup of one-to-one mapping, but that's not the case with CompletableFuture. So, for example, let's get rid of all of that. We have our future. We create a second one, for example. And now we can complete them without really involving any particular threads. I'm completing them from the main thread. And the second one, maybe not exceptionally. And now I can create another thread pool, submit another job that will actually complete one of my features with, again, with another value. And I can copy-paste that line of code a bunch of times. By the way, that's a really poor way of running something asynchronously, just to illustrate a point. OK, good point. I will stick to the top of the screen. So, look, those features are now completed by the main thread and by those random threads over there. They can be completed by the arbitrary number of threads, and this complicates things a lot. Sometimes there might be no third-party threads involved, which means there is no direct mapping. One feature can be never completed by any threads, or it can be completed by the same thread or by something else. There is no connection, and this creates problems, because you can't just say cancel, because there is no way to tell what's actually running, where's actually operation running that will complete that future. The future is just a holder of a particular value. And what can we do about that? Well, nothing. There's something we need to live with and accept. Reactive libraries can propagate those signals up to the source, but that's not the case with CompletableFuture at all. And actually, if you start thinking about those scenarios where you have those huge trains of commands like here, let's say we call cancel at the very end, after then run. So what do we actually cancel? Do we cancel all of the operations along the way? Keep in mind that those are intermediate features getting created after each step. They can be canceled separately. They can be completed separately. What do we do with that? As you can see, that's all complex, and that's something you need to forget about. That one-to-one mapping is not present with the future itself. You can hack it. So in my library, I'm hacking it this way. but I can make certain assumptions there that there is this one-to-one mapping. But in most cases, that's not the case, and please don't copy-paste that. And that's the first thing, the cancellations. Second part, which is, it still amazes me, it's quite surprising, it's two very peculiar methods from CompletableFuture, all of and any of. So imagine a simple use case where you have two futures. And one of the basic use cases would be to, for example, wait for all of them to complete and return results. And you might be naively just browsing the API and looking for something. So let's do that. Oh, and the first one that popped up is all off. Sounds good. So we provide 1, 2, and we get something in return. Let's call it CF3. Wait, so that's CompletableFuture of void. I said explicitly, I want to wait for all those two futures to complete, and I got void in return, but they are integer. What's going on? Let's have a look at those signature. And the signature is a bit weird, because there is a var args accepting CompletableFutures of any type, which means technically I could make that one, CompletableFuture of a car, and suddenly it works. It compiles, and there are no issues with that. And it returns void. I don't know how about you, but my impression is that if I want to wait for a list of futures, I would pretty much never pass the futures of different types there. And even if I did, I would rather expect them to be returned in the CompletableFuture that was returned by the method. For example, in the form of a list. But that's not the case. But this gets even worse. So let's actually try to use that. So we have this CF3, we call join. But before we call join, let's try to print out what's inside. So we declaratively say, then accept a function that will be called when it completes, and wait for it. Well, we didn't complete them in any way, so there's nothing happening. We have a deadlock. Let's fix that. Let's complete them manually with 1 and 2. So as you can see, we did, I completed the same one twice. So as you can see, I completed both of them, and that one completed as well. OK, makes sense, that works. It didn't return any value, though, so that's a bit problematic. But now, let's say I add an exception here. So let's say the second one happens to complete exceptionally. There was a null pointer exception somewhere along the way. So I don't know what's your expectations towards the behavior of such a function, but if there is an exception, and I know that at least one of n futures can't complete, then we have an issue, and pretty much we could throw that exception immediately. So let's see if that happens. Let's remove the first one. So the first feature will never complete, but second one will complete immediately with a null pointer exception. And it doesn't complete. Because as the name suggests, it's all off. It waits for all the futures to complete. Even, it doesn't matter if they complete with actual value or with an exception. They all need to complete. So we have another deadlock. But that's not usually there is some use case for that, but in most cases I would expect, the exception to be propagated immediately. So what can we do about it? Well, nothing. We can stop using that method. But actually, let's try to redo it pretty quickly, because when I write asynchronous code, it turns to repeat quite often. So we have that method. So there is this all off. How do we fix that? Let's introduce a generic type, first things first. Let's make it return a list of t. A CompletableFuture with the list of return values. And let's make that accept a list of completable futures of that particular type. Looks much better already, because at least we are restricting ourselves to always using only the same type. So how do we rewrite that? And actually, it turns out we can reuse the all-of method, but we would need to do some acrobacy to make it work. So we could go for all-of, and we need to pass the var args here, which means we need to convert that to an array. How do we convert to an array? We need to call the toArray and pass a new array. And here's a quick question for you. What value should I put here? Sounds reasonable to put the size of an actual collection, right? Because we know how many futures do we have, right? Does it make sense to you? Sounds reasonable, right? So it turns out it works, it's fine, but it's slightly better to go for 0. And why is that? Alexei Shipilev will explain it to you. But pretty much the trick is that the cost of initialization of each array element, well, is non-zero. But if you start from 0, you don't pay that extra cost of initializing all the elements in there. So we had that future. And it's a combined future of all. What can we do now? So once this one completes with void, with nothing in height, we know that all those futures in that collection is actually completed. We can reuse that fact. So let's call then apply. That's our void here. Let's totally ignore that. And now we can just go straight for our original list, repack it, because it's safe to do. They already completed. We can do that. And now we just collect it to list, and here we go. Here's your combined future that has a completable future of list of t inside. But there's one slight issue with that. We can already use it. Let's replace it with our all-of. And it works. Well, we would need to put that in an array in the list. And that doesn't match, so to CF3. Let's run it. It looks a bit better. But it still doesn't complete. The exception doesn't short circuit. So the trick is to add one more operation in here. So we can iterate through those initial futures. You can for each them and say, whenever that one completes with an exception, then complete that original one exceptionally. And that's quite a common idiom that I happen to use. So we complete with a variable. And now once we run it, it works as expected. The exception is short circuits immediately, and everything is returned. So as you can see, it's pretty messed up. It requires some extra work, but you can get it done. But most important part for me is so that you understand actual of the surprises that those methods actually involve. I have some help for myself here. Just ignore those slides. So for example, that's code from one of the testing libraries. There's a huge chance you might be using. It's using it in a row. At some point in time, it was using it in a raw form, all-of, and it had the same issue. So you would start multiple containers. One of them would fail immediately. Others would be downloaded, for multiple seconds. But you would still wait until all of those operations are completed to tell you, sorry, it couldn't be done. Another interesting method is CompletableFuture any-of. And you might think, what could go wrong here as well? So we have that all-of already. Let's see how does the any-of look like. It's kind of similar because it accepts a list, var args of futures. They are all, again, different types, which is, again, a bit weird. But there is a use case for that. And it returns CompletableFuture of an object. OK, it's slightly better. right? Because if I have an object, I can do my casting, I can do some magic. I can, if I am on the new Java 17, I can use pattern matching and okay, but still not good. So let's try to use that. CF1, CF2, any, let's call it NEF. And if we do NEF, again, then accept, join and wait, you will see that we have a deadlock because none of those features completed. So let's complete one of them manually with the value 1. We got the value 1. That works. We got the value. Let's complete the other one with the value 2 to make it clear. Oh, the first one completed first. Great. Let's say that one of them completed with an exception. What do you expect? Okay. Okay, great. So we have 2 features. One failed, one completed with 1, and NEF returned 1. Okay, that's great. Let's switch those spots now. What do you think happens now? What you would expect to happen from a method like NEF? I would expect to wait until one feature completes with a success and gives me some result. But if I run it, I get an exception propagated. It turns out that NEF doesn't care about success. Okay, that sounded like a coachy or something. It doesn't care about success. It cares only about the first one that completes. And again, that's a bit unintuitive, don't you think so? So again, that's something that you need to keep in mind while working on that. There is a way to rewrite it. It's a bit more complex than the previous one. I mean, conceptually, because you need to first iterate through create a new feature, iterate over all the available features, manually force the new one to complete, and then ensure that in case all of the features failed, then complete the original one.
Back to IntelliJ and the comment line with the CF1.
You want me to comment the line 18? Okay, so in case we complete only one feature with the number 2, I expect to see the number 2 being printed. Because it's NEF, and the only one completes the one with value 2, and that's what you see in the code. Okay, thank you. So that's another interesting part. But the most interesting part is coming now, which means CompletableFutures versus threads. That gets quite interesting. And again, in JDK 1.5, it was pretty straightforward. You would create your own thread pool. Let's say with 4 threads, call it executor. You go submit. You submit something that returns 42. Let's make it a bit more interesting. So let's create a method return with delay. We return t something. You return t. You add thread slip. Let's say 2 seconds. Okay, I shouldn't be so allowing that interrupt the exception, but I hope you can forgive me that. We have that feature. You submit, you get. You need to process a bunch of exceptions, and you can run it. You can run it, it will never stop, because those thread pools feature non-daemon threads, and the JVM will never close, so I need to shut down this additionally. And of course, I need to call that method with delay. It works much better if you use it, return with delay. Say 42. So after 2 seconds, the value gets returned and the process stops. I didn't print it out, but I hope you trust me that it was properly returned. But with CompletableFuture, it gets a bit more complex. So imagine you have this CompletableFuture running, and you join multiple methods all around the place. There's the run async, then run, then run. And the question is, which thread does actually run those methods? Because when you receive a CompletableFuture, okay, probably it's being completed by some other thread. But as we know already, those can be multiple threads. And if I call run async and then run or something, it all actually returns. Let me show you. Completable. Supply async. Let's make it return with delay 42. There is that future. So as you can see, you can do something like then apply, then run something else. And it's kind of obvious that at the beginning, it's being executed by that particular thread. But imagine what happens if that future is completed before I even get to add that method to it. Let's see if that's the case. So we have this thread running here for 2 seconds. Let's say that in this return with delay, I will print out the thread name. Let's say I do then apply, and that apply will involve pretty much not doing much, but just calling again the same like here, and then joining and waiting for the operation to complete. So as you can see, it's executed on a common pool worker because I use that variant which schedules everything on the common pool worker. Let me add a custom thread pool here that I will submit here. And again, it's, as you can see, pool 1, thread 1. OK, that works. This is the same thread. OK, pretty clear. But now, here comes the fun. So let's say that future is actually empty. So we create a new CompletableFuture. Nothing completes it. There is no thread that could complete it. So where do you think this will be run? Do you have any ideas? I think that there's no point in shouting, but just at least try to answer in your heads. Where could this be potentially run? So let's have a look. Well, it's running nowhere because I didn't complete that future. So let's make sure that it's completed. With the value 42. That's not needed anymore, at least for now. Look what happened. It turned out that it was executed by the main thread, the same thread that's running that method. But that then apply method is returning, I'll make it crystal clear here, it's returning a future. And that future one, if I join on it, it tricks you into thinking that that's fully asynchronous. You are receiving a future, you are expecting it to be asynchronous, to be non-blocking, but it's blocking anyway. If I add here a sleep, thread sleep, let's say 10 seconds, it will block the main thread for 10 seconds. It's a bit undesired, isn't it? And this is a big surprise. That's also something that you need to think about. Naturally, there are solutions to that. And we'll go over that in a second. But let's actually dig deeper. You've already seen, I spoiled some fun for you, that if you don't provide a custom executor, everything will be run on the fork join common pool. But let's actually try to dig deeper. Where is it scheduled? The default one. You will see that somewhere in here, there is something like async pool. And that's the default one. And look, what kind of magic is here? So there is this use common pool Boolean value, which checks if the parallelism of the fork join pool is bigger than 1. OK, makes sense. If we are capable of running something, at more than 1 parallel level, it's OK. We use common pool. which we will talk about soon. But otherwise, use fair per task executor. So if your computer happened to have only one CPU because you are living in the past, actually you are not using a thread pool at all. You are using something that implements a thread pool, but it's creating a new thread each time you execute a runnable. So a bit undesired, isn't it? Naturally, there used to be a very good use case for that. So if you're indeed living in the past and you have a computer with one CPU, that's actually a bit, that's okay. But we are not living in the past. Or maybe we do. Because if you go to the world of containers, Kubernetes, and the cloud, suddenly we live somehow in the past there, because you might be restricting your CPUs to your containers. And there's a quite common issue, because those values internally they are derived from, what's it called, get available processors. It's based on that value, and that value not only can just return 1, won't return you the number of physical processors, can also lie to you, because if your processor is with hyperthreading, it will actually return a different number than the actual value of physical core is. Anyway, so you're in the world of containers, and you restrict your CPUs, and you restrict to 1, and suddenly the default thread pool changes into something that's not really a thread pool, but just new thread, new thread, new thread. So as you can see, it's a bit undesired, and I hope you didn't know about that. But luckily, there is a solution to that issue. So there's this method then applied, and then something else, which returns a future and seems to be async, but isn't really. I mean, cannot be. So if you really want this method to be fully async, you need to add async to that. And now you have guarantees that this async method will be really, returning future will be really async. But hey, I didn't define any executor service or anything like that. Where does it actually run? So I didn't pass any executors there. Isn't it weird? Does it run in the cloud or where? Is it serverless? So it turns out that if you start digging, if you start looking at what does it return, let's have a look. We actually get this common pool worker. And there's a very special and very interesting thread pool available in your JVM. The standard thread pools look like that. There is a thread pool, in front of it there is a task queue, and there's a concurrent queue. You have multiple consumers from that queue trying to take task, and there are usually multiple producers that are trying to push something into that queue. From the concurrency and performance point of view, this is very undesired, because there's a lot of contention on the receiving side and on the other side when you're adding something to the queue as well. So they figured out a new experimental design for the fork-join pool, where each thread gets a separate queue, and the tasks are effectively round robin at the very beginning for the task between every thread and its own queue. And it has a few other cool features, but there's something special about the common pool. There's a reason why there is a central common pool in the whole JVM. Because it's one static instance, it's over there, and it's initialized with that number I showed you earlier, that runtime available processors. Because it's supposed to be very efficient at running your CPU-heavy workloads. So that's why in the center of the JVM there is this one thread pool that has the number of threads that's correlated with the number of CPUs that you have on your machine. Because if you're running CPU-heavy workloads and you have more than that, you're actually paying the penalty of context switching and you're not getting any speeds up. You would get a bit more speed up if those were blocking operations. But that fork-join pool isn't used for that. If you put some blocking operations without tools called managed blocker, you will waste resources of that precious pool for blocking operations and effectively waiting. And that's something really, really undesired. But if you go back here, you'll see that If you use supply async with the default design and don't provide any custom executor service, which I will do right now, it pushes your tasks into the command forwarding pool. And you noticed earlier that when I created my own first CompletableFuture by submitting a job to a random pool for CompletableFuture supply, I didn't provide my executor. It defaulted to the forwarding pool, the common one. Guess what? The same applies with parallel streams. They are using the same thread pool. Guess what? If you've seen Andrew's talk, an hour ago, you would know that the project Loom and all those virtual threads are scheduled on the common forwarding pool as well. So I'm not sure how it looks immediately right now, but if you push blocking tasks into that forwarding pool, you end up in a very undesired situation because you can not only impact your own code, but code running on virtual threads and the code running on parallel streams. If you live in the past again and you have application servers that were often running applications and they were just one big JVM process, another application technically might be, even if you are doing everything correctly, there might be another application impacting performance of yours. So the solution to that is to always use those async options, ideally with your own thread pool of choice. Then apply and other methods without async are perfectly fine if you are running some trivial workloads. So for example, if all I want to do here is essentially just, for example, increment an integer, that no one cares, it's fine if you do it in the main thread and it blocks, that's perfectly fine. But you need to pay attention whenever there is something bigger than that. If there is something juicier, if you are running some, if you are calling other services, some calling database, if you are waiting for on locks, something else, that's something to look out for. And that I showed you already. And the very last thing I'd like to show you today is funny case of apply to either versus exceptions. So let me get rid of that. Let's create new CompletableFuture, integer, cf1 again, cf2. If I want to achieve semantics of perform computation or the future that completes first, there is this apply to either method. So what I do is I say CompletableFuture1, apply to either, CompletableFuture2, and here I get to provide a function that needs to be applied to the result of any of them. And this, as you can see, this sounds pretty sane. Let's see what do we get in return. That's CompletableFuture with an integer inside. Makes sense. So let's go then accept, join, see what happens. Well, of course, the deadlock happens because there is nothing, I didn't complete any of them. So let's do it again. Complete it with 1, complete it with 2. It's the same one, sorry, but it shows what it's supposed to show anyway. Let's complete this one exceptionally. With the null pointer again. Guess what? Everything works correctly. Because guess what? Apply to either, and that one has a value. Let's switch places. You know what to expect, right? Yeah, here comes the exception. Apply to either. So, and the way it treats it is it tries to apply to either, and the first one that completed had an exception, so it tries to apply it to that method, to that function to an exception, and here you go. I don't know what you think about it, but I think it's a bit unintuitive and undesired. And of course, you can kind of play around and try to rewrite it, and you had the right tools to do that already. But those are those 4 main things that I want you to remember about. That computable futures, they can't really be cancelled because there is no threads that back it. Those can be arbitrary threads. You need to remember about the threading model and those APIs which, with the design that's a bit promoting bad practices. And about any of, all of, and apply to either, and the way they propagate exceptions. Well, they treat exceptional completion as on the same level as normal completions, which is not always what you want. Because in most cases, probably you care only about the actual one, that the values that completed with success. And unfortunately, there are no tools in the JDK itself to give you that kind of behavior. You need to write it, write them yourself. But that's not that big of a deal, luckily. And that's pretty much all what I wanted to show you today. So I hope you learned something new. Those are just 4 things, but quite important ones. Well, and just follow me on Twitter. And here's the link to the slides. Thank you.